So this is the start of Unit 8, which is going to be a continuation of talking about energy that we did in our last unit. This is a unit about thermochemistry. So this is specifically related to heat absorbed or released in a chemical reaction. And then a heat is a form of energy, so that's why we talk more about energy. I want to introduce the idea of the law of conservation of energy here. It's the same as the law of conservation of mass. Energy cannot be created or destroyed. So if it's added to reaction, then it needs to come from somewhere. If it's released, it needs to go somewhere. And that brings us to endothermic and exothermic. We talked about this last unit, but you can go ahead and fill in the definitions. You can do this in your own words. Endothermic is a reaction or a process that absorbs heat. And exothermic is a process that releases heat. In an endothermic reaction, remember we talked about this last unit, an endothermic reaction will be cool to the touch, and that goes to the law of conservation of energy, because if we need heat to go into the reaction, then it needs to come from somewhere. It comes from the surroundings. When the heat is taken out of the surroundings, that means it gets colder. The surroundings gets colder. So we're going to talk about potential energy diagrams. Potential energy diagrams are talking about the actual system. So last unit, we did a lot of work with endo and exothermic with like the surroundings. If we take the temperature of this and it gets colder, what happens? Okay. Potential energy is talking about the actual system. This is not the surroundings. So this is taking the potential energy of the chemicals that are reacting, the process that is happening. So there are a few things we want to label on here. First, we have the energy of the reactants. Notice that energy is on our y-axis. So energy of reactants is here. The energy of our products is here. The difference between them, so if I just kind of extend this line over here, the difference between them is delta H. Delta H is change in, delta is always going to be change in energy, enthalpy. So change in enthalpy is the difference between the products and the reactants. And enthalpy is a form of energy. So delta H is always going to be equal to the energy of the products minus the energy of the reactants. So here we can see that the energy of the products is higher. Now remember, this is the actual system, not the surroundings. So if the energy of the products is higher, this is going to be endothermic. So this curve right here is a generic endothermic reaction. If delta H is the energy of the products minus reactants, and the products are higher, right? It's a bigger number. That means this delta H is going to be positive. So if delta H is positive, that means it's endothermic. I'm going to show you an exothermic one in a minute, but we'll just put this together here so that your notes are complete. If delta H is negative, it's going to be exothermic, and I'll show you what that looks like in a few minutes. So another thing we want to label on here is something called the activation energy. And we represent that as EA, which is the activation energy. And that's the energy required to make the reaction happen. On our graph, we need a certain amount of energy to make the reaction happen. So we start here on this little dotted line that I made. And the most energy we would need is this little bump. So that right there is the activation energy. We would have to add enough energy to go from where we start, that energy of reactants, all the way to the top of the graph. There is a way to lower the activation energy, and that's by using a catalyst. So you may have heard catalyst before. An enzyme is a catalyst that a lot of people are familiar with after they take biology. What a catalyst does is it is something that you add to the reaction and it lowers the activation energy. A catalyst is not used up in the reaction. Okay, so it's something that you add at the beginning and then it is regenerated at the end. But on your graph, you can just draw, it's going to start at the same place and it's going to end at the same place, but it's going to require less energy. So it's going to lower the activation energy. So you can draw a catalyst line, something like that. And you don't need to be specific about how high or low it is. That makes the reaction go faster. So a catalyst is going to speed up the reaction by providing a lower activation energy. It provides a different reaction pathway, and that requires less energy. So that's what a catalyst will do. And there are a bunch of different types of catalysts. That's beyond the scope of this course, but it is something you'll get into if you take more advanced chemistry classes. So that's all we have to label. Now let's take a look at an exothermic one. This is exothermic, and you can see that because the energy of the products is lower than the energy of the reactant. So that must mean that energy was released because we have less energy at the very end. We can still have our delta H, but it's going to look a little different. It's above the product line. We hear delta H was below the product line. And that's because delta H here, energy of products minus reactants, is going to have a negative number because it's exothermic. We can also show our activation energy. It's probably not. And we can show a catalyst, starting at the same place, ending at the same place, but taking less energy. So that is potential energy diagrams. They're very useful for a lot of different things, but we're just going to introduce them here.